All right. So, after this recap of the concepts that we have seen in cosmology, and after having expanded that context by making the all expression in a fully general relativistic scenario, let's now continue with something specific and more interesting for our case, which is the study of the perturbations in presence of scalar field. Our dark energy. Okay, now we have the case in which we have dark energy. For we are going to be interested in a multi-component universe. In which we have more species at play. For example, we are going to have the big M, which stands for radiation or matter, plus our dark energy field. So we have these two species. And we can use what we had before, but we have to keep in mind that for dark energy, we have an equation of state, which is dynamic, can be dynamic. If it's not, might be the, for example, if it's static, would be the cosmological constant, -1, okay? If, otherwise, it's dynamic. And then the same will go for the sound speed, okay, for our dark energy field. So that's key. And this is explain you why we can use all of those equations within the context of dark energy. But we need to keep in mind something, that dark energy is a fluid, right? And what can fluid do? What they could do? They could cluster. What does it mean? That in the end, we are going to have an expression characterizing the perturbation of the field. So we are going to have a background solution for our field that carries basically the expansion, characterizes, enters into the description and causes the way the universe is expanding, so providing acceleration. But we have the possibility for this fluid to cluster. Therefore, we can have regions that have more dark energy with respect to others. Okay? And this fluctuation can grow or decay. Okay? According to some equation. Nice. So these are the key points that we are going to consider. So now going back to our multi-scale, multi-component universe, we are going to have the total density fluctuation that is going to be given by the weighted sum of the density fluctuations. So we did this sort of derivation for W. If you go back to your lecture notes, you will see that we computed already W effective, which is defined as P total over rho total. So if you just substitute here the total contribution of pressure and density in a flat cosmology, in the end, you just have realized the fact that your effective equation of state parameter, so the one that is characterizing the Friedman equations, okay, so the dynamic of the universe, is going to be a weighted sum of, with respect to the omegas of each component. Okay, so you have the equation of state parameter for the fluid you're considering, and you have the weighted sum. Okay, this gives you your W effective. Similarly, is done in deriving this expression. Okay, there's no difference between the two. Then, again, during doing the same, we have the total sound speed, which is going to be given by the summary of the sound speed of each individual components with respect to the perturbation density, the fluctuation density, normalized with respect to the to the total. And it can also be written as E square delta E over sum of E omega E delta E. I just substituted that. Okay? Nice. And then again, just keep in mind that you have this very convenient expression that allows you to link H prime to the equation of state parameter, or the equation of state function, if it's varying as a function of time, which is as well written like this, just by using the definition of the curly H, minus 1/2, 1 plus 3W effective. Okay, that's very convenient. Again, this is just coming from the Friedman equations, and by using the relationship, and just by using P equal to W rho. Okay, is a direct result of that. Nice. Now that we have that, okay, multi-component universe, we can go back to our Einstein equations and to the continuity equation. So there is going to be a little bit of reshuffling and massaging of the equations to make them more usable, okay, for further derivations. But I'm not going to, change the physics or introduce anything specific. So massage equations. So we start with the first one, and I show you what we do it, and I show you the details, because if you look at the books, it's always a mess to navigate them, because somebody used the derivatives with respect to the tau, which is what we did so far. Somebody used d over the n, which is extremely convenient, and that's what we are going to do. And everybody is using prime. Okay? Therefore, if you look in a book, then why there is this H not and blah, why? You don't understand? The reason is because there are these steps involved. Okay? So let's just give a look at that. Good. So let's start with the Einstein equations. So we get the mu equal to 0, 0. So that's the first one up there. And this is just, I just write it here so that we have a nearby, plus 3h bar phi prime k minus h phi k equal to 4 pi g a to the power of 2 t delta k equal to 3 half h to the power of 2 delta k. Good. Then what we do? We make this change of variables. Okay, so we are going to transform. We are going to from characterizing the evolution of our equations, not anymore with respect to the conformal time, but with respect to n. Okay, I recall you that n is defined as 1 over h bar over the tau. Okay, there is this guy here. Okay, this creates a lot of confusion if you want. Okay, what does it mean? It means that now we are going to transform. Sorry, that's the n, because that's the. That's d over the n. Okay, I already did the derivative. So what happens is that we are going to plug this guy into these equations. Okay, therefore we are going to have the d over the tau is going to be equal to h d over the n. Therefore our primes will become an h times the prime operator. Okay, that's it. If we do that, then we are going. Then I just extract p to the power phi. So I'm dividing this expression through k as well. we obtain phi of k is equal to 3 half h to the power 2 over k square. No, this is delta, because that's the potential, plus 3 h over k to the power of 2, h phi k minus phi prime. Okay? Here I use the, from here to here I use the Friedman equation again. Okay? So Friedman, you see from rho I extract h. Okay? And then that is a constant that they just drop out. Okay? Then what I do is that from here we arrive at this expression. Okay? Now you see that we have this guy here. Okay, interesting scale to the power 2. I think this is wrong. Okay, I have a doubt here now. But anyway, you see that we have this ratio between the two, and we just define lambda f as h over k. And we plug it here. We just use this definition here. What we obtain in the end is phi k equal to 3 lambda to the power of 2. I think I forget 2 here. Here. Lambda, yes, then we have 1 half delta k plus phi k minus phi prime. So that's equation 1. No physics involved, no assumption, no anything of that. Okay? We just changed the time variable and we defined this guy, this lambda. Okay? So you see, if you want, it is the wavelength associated to this k. Just normalize with the expansion of the universe, with the term containing the expansion of the universe. Okay? And it has a little bit more manageable structure. Then we go for mu equal to 0e. So that's the second equation. And we do exactly the same. So we get this expression. We change the time variable from tau to that n. And what we exactly following these steps. Okay, you find them in the lecture notes. I will not repeat them here because they are just identical. And we obtain phi k equal to phi k minus phi half lambda square 1 plus w effective, and then I introduced this curly k, and that's the total. That's the total one. Okay. What's this guy? What is curly v? Well, the curly v is another quantity that I introduced like this one. Okay? Here I just define this quantity. Here I just define just the divergence of the velocity rescaled with respect to h. Again, no physics is involved, just change of variable for the time component, and I introduced that guy. That's this expression. Okay, that's equation 2. Then we can have the equation 3. So let's put it here. 1, 2, equation 3. That's just as trivial as that. And recall that in general, if in a non-general relativistic case, we would have that. Now, not. Okay? Good. And then we have, and this is unchanged, and then we have the Poisson equation. Which was the equation A? Yes. The Poisson equation, and we do exactly those steps. Remember, Poisson equations was coming by combining the first two that we did earlier. We change the time variable, and that's it, nothing else. And what we obtain is phi k equal to 3 half lambda to the power of 2 delta k plus 3 w effective plus 1. Then we have our curly v lambda to the power of 2. Now, just to show you, just to stress, here is some important physics. Look at this guy. That's what you can observe. What you observe in reality is not this delta k, so it's not just the fluctuation of the perturbation of the density field, but there is this general relativistic contribution, okay? And that's the observable. Is a gauge invariant observable. Let's put it here. Okay? So whenever you're in a general relativistic context, this guy is there, okay? Good. Nice. Then we can continue with our other beloved expressions, and we do exactly the same. So we are going to have the equation 5, which is just going to read delta k prime plus 3 cs squared minus w delta k equal to minus 1 plus w. Then we have the curly velocity, curl plus 3 phi prime k. And in the end, the Euler equation, which was equation 6. Again, nothing happened here. Curly velocity prime equal to 3 w minus 1 minus w prime 1 plus w minus h prime over h. Curly velocity plus 1 over lambda squared cs squared over 1 plus w delta k plus w k. That's our Poisson equation. Energy. Poisson equation, and I want to stress that this is a force equation. Force equation, so it's, if you want, is a generalization of Newton's law, in which you have what? Look this one. This is an acceleration. That's related to an acceleration, right? It's a time derivative of the divergence of the velocity field. So that's related to accelerations. Acceleration of our fluid, which is caused by what? Is caused by a pressure term there is CS here, that's the associated pressure. We have gravity, notably phi, not the time components, only the space component. And then we have a friction term. friction term that you see, it's a friction because it's multiplied by our variable theta. Okay, so the acceleration can be slowed down because of the friction, which is caused by the expansion of the universe, and it has some term depending on the properties of the fluid we are considering. It has pressure, so pressure can push or pull, no? You know, it's like a force, and then we have the gravitational contribution, so gravity can cause acceleration in our fluids. So these I want to stress because these physical concepts are going to be relevant later, and focus on this guy, the pressure, the friction contribution, and the gravitation contribution, because when we are going to have coupling, these two terms are going to be modified. Okay? Good. Then, let's pause a second on these expressions, because they are the ruling equations. Everything depends on that. Okay? So let's try not to cancel them. I don't know if I will be able to arrive at the coupling today. But at least I will give you the core equations, and then we will introduce coupling next time. Then what we do? We have our set of equations, and we combine them. We combine them. And we obtain this one, coming from, now I tell you from where it's coming from, 3cs total squared plus 1/2, 5 minus 3, w effective, p prime plus 3 plus lambda to the power of minus 2, cs t to the power of 2 minus 3, w effective, phi equal to 3 cs total to the power of 2 minus w effective. And then if we have the red contribution there, we would have these guys. Okay, this would carry the perturbation, the departure from general relativity. And this is being obtained by combining 1, 2, 5, and equation 6. Okay, have fun by doing the steps, but this is, there is nothing, no physics hidden there. Then we have for the R, if we are taking a relativistic species, then we have the equation giving the perturbations of the density, so the density perturbations, W effective, delta prime R plus 1/3 lambda minus 2 delta R equal to 4/3 lambda squared phi plus 2, 1 plus W effective, phi prime minus 4 phi dot dot. That's for radiation. Remember that we are in a multi-component universe, okay? Now, and then Cs is equal to the power of 2 is equal to W, which is equal to 1/3. Okay? And that's for the case of lambda much smaller than 1, so small scales, so that's sub-horizon scales, and by setting sigma equal to 0. Why is this relevant? Why do we care about? Well, think about radiation domination. Radiation domination, we have observations. They're coming from the cosmic microwave background. But what do we study in the cosmic microwave background? Okay? We study temperature fluctuations that are coming from the combination of gravitational redshifts, the velocity, the Doppler effect of the velocities, density perturbations, and all of that, which is captured by this equation. That's fully general relativistic. We are carrying the information about what the gravitational potential is doing. Therefore, this equation can be written in terms of temperature fluctuations, which are our observables for CMB observations. And this equation will look like that. Now, I didn't change the variables, sorry for that, so that with respect to the conformal time. Equal to k squared over 3 phi k minus 3 phi k over the tau squared. For theta, temperature fluctuations. Okay, so that's defined as dt over t of the background. That's what you observe. And you basically transform from the density fluctuation of photons to that. Okay, this is coming from the board. Okay. This is just to stress the fact that we have fully general relativistic approach, we can treat photons. And then, just by linking the density fluctuations to the temperature fluctuations, we have this expression, which is something observable. Okay? Observable. Last one. We have the equation for matter. So here we did it for radiation, now we do it for matter. So we go in matter domination, and this is relevant for what? For studying galaxies, for example, the distribution of galaxies on large scales, okay? For doing clustering measurements. So again, something that we can observe. Plus 1/2, 1 minus 3 W effective, delta prime matter equal to minus lambda minus 2 phi minus 3/2 1 minus 3 W effective phi prime minus 3 phi to the power of 2. That's for, I wrote photons, yes, radiation. This is for matter. Okay, dust. With W equal to 0. Where is dark energy here? Here. And here. Okay, so that's the effective one. It contains the effect of dark energy. So you see that dark energy has an impact on the distribution of galaxies. Okay. What is missing here? An equation of this sort for dark energy, right? Because it's a field, it's dynamic, and we need another equation that traces the dynamics of dark energy. Because under certain models that you build up, you can have a clustering. So dark energy could be clustering. And if we measure the clustering contribution that is reflected on the matter distribution, because that's we cannot see the field of dark energy, we don't see that directly. We see its effect on the universe and in this case, on the evolution of the metal perturbations, then we can have a full picture and perhaps capture not only the evolution of the equation of state of dark energy that impacts the expansion of the universe, but also, so not only departure from W equal to -1, okay, but also clustering. This would be another feature that would distinguish a model in which you have a cosmological constant or you have dark energy. Okay, so structure formation, cosmic structure formation is extremely relevant for trying to understand the physics of the expansion of the universe and for dark energy or the cosmological constant. Okay, so we can stop here. I leave you with these equations that are the super relevant ones. Okay, so also this one. These ones are just coming from there, and it's just some mathematical reshuffling for convenience. And these are coming from the combination of these ones. Okay? Here you have the full picture with one thing which is missing, that is an equation of this sort valid for dark energy. And we are going to derive that during the next lecture, so we are going to constrain the evolution of dark energy. And we are going also to introduce a coupling. So we are going to have a modification on, guess what, this equation. Okay, so we are going to have a coupling term that is going to enter into the energy conservation and into the Poisson equation. Okay, good. So we can stop here. Thank you very much, and I'll see you later. Oh, sorry? What do you prefer? 2:30 is fine? Let's stick to 2:30. Okay.